Dear students, in this class let us discuss about the division algorithm as well as Euclidean algorithm. What is division algorithm? Division algorithm. Division algorithm states that given A and B are any two integers with a B greater than 0. A and B are any two integers with a B greater than 0. Then there exists a unique pair of P and Q, unique pair of integers P and Q such that A equals BQ plus R with a 0 less than or equals R less than B. Moreover, if R equals 0, then B must divide A. So this is a division algorithm. A and B are any two integers with a B greater than 0. Then there exists a pair of integers P and Q such that A equals BQ plus R with a 0 less than or equals R strictly less than B. Then if R equals 0, R equals 0 if and only if B divides A. So this is a division algorithm. How to prove this one? This is a manage. Proof is a manage. So far, you can construct a set of non-negative integers. You can construct a set of non-negative integers S such that S equals set of all Y, where Y equals A minus Bx. Y equals A minus Bx, where X is an integer and Y greater than or equal 0. Why? Because S be the set of all non-negative integers. So S equals set of all Y such that Y equals A minus Bx, where X is an integer with a Y greater than or equals 0. Clearly this S is non-empty. S is a non-empty set. S is a non-empty set of non-negative integers. Since S is non-empty, this S has a least element. Let S has a least element since S is non-empty. So surely this S has a least element. Let A minus BQ be the least element of this S. A minus BQ be the least element. Least element of S. A minus BQ be the least element of S. Let R equals A minus BQ. Let R equals A minus BQ. R equals A minus BQ means what is A? A equals BQ plus R. Enough. A equals BQ plus R, but R equals A minus BQ. It is of the form A minus Bx. Here Q is an integer. Why? Because we can choose Q as an integer. Then A minus BQ, it is of the form Y. So Y greater than or equals 0. Surely this R greater than or equals 0. Okay. So the first inequality is called 0 less than or equals R is already proved. Why? Because R equals A minus BQ. That is our choice. Then A minus BQ is of the form Y because Q is an integer here. Then that Y is greater than or equals 0 is by our choice. Hence R greater than or equals 0. Now to show that this R less than B. This is our second requirement. R less than B. For that, if R greater than or equals B, what happens there? If R greater than or equals B, R greater than or equals B means this R minus B should be less than R greater than or equals B, then R minus B should be less than R. But what is R minus B? But R minus B equals, what is R? A minus BQ. It is A minus BQ, R is A minus BQ, A minus BQ minus B equals A minus, take B outside, B into Q plus 1. A minus B into Q plus 1. B is commonly taken outside. What is Q? Q is an integer. Q plus 1 is also an integer. Then A minus B into Q plus 1 is of the form A minus Bx. So surely this should be present in where? A minus B into Q plus 1 presents in Yes. A minus b into q plus 1 presents in S means r minus b also presents in S. But what is r minus b? R minus b less than r. What is r? A minus bq. So r minus b presents in S, but r minus b less than a minus bq. But we chose that a minus bq be the least element of S. So there is a contradiction. This contradiction is due to our wrong assumption. Therefore, r should be less than b. So this is the second part. So 0 less than or equals r less than b. Okay. So the first part is finished. Now, for the uniqueness of Q and R, P and Q, this Q and R, the uniqueness of Q and R. What is the how to prove the uniqueness of Q and R here? So, for proving the uniqueness, first we assume that if possible, there exist two such elements. That is, there exist the elements Q dash and R dash, the pair of integers Q dash and R dash fall in such that A equals 1, A equals BQ plus R. So it is A equals BQ dash plus R dash and A equals BQ dash plus R dash. But we have also A equals BQ plus R. If possible, there exists another pair of integers Q dash and R dash fall in set Q dash and R dash such that A equals BQ dash plus R dash. But here A equals BQ dash plus R dash as well as that A equals BQ plus R. That means this BQ plus R equals B dash plus Q dash. BQ plus R equals BQ dash plus R dash. That means B into Q minus Q dash equals R dash minus R. Bring BQ dash to the left side, R to the right side simultaneously. BQ minus Q dash equals R dash minus R means this B must divides R dash minus R. Okay. Why? Because R dash minus R is an integer multiple of B. Why? Because Q and Q dash are integers. Agreed. So B divides R dash minus R means this B less than or equals modulus of R minus R dash or R dash minus R. Why? Because A divides B should implies mod A less than or equals mod B. Agreed. A divides B, that means mod A less than or equals mod B. So that means according to that argument, B divides R dash minus R means B less than or equals modulus of R dash minus R, which is impossible. Why? Because R less than B. So this is a contradiction. So this is not possible. That means here R dash minus R equals 0. If R dash minus R differs from 0, then B less than or equals R dash minus R, which is impossible. Thus R dash minus R equals 0 means R dash equals R. Okay. When R dash equals R, this equation 1 becomes B into Q minus Q dash equals R dash equals R means 0. This possible Q equals Q dash. Why? Because of the choice of B. Since B never becomes 0. Why? Because B should be positive. B greater than 0. Therefore, Q equals Q dash. Hence, R equals R dash. Q equals Q dash means the uniqueness is preserved. So, this is the division algorithm. Clear? Now let us consider another important argument, which is known as Euclidean algorithm. Euclidean algorithm. What is Euclidean algorithm? Euclidean algorithm states that given A and B are positive integers, A and B are foreign surplus positive integers, such that B does not divide E. B does not divide A means A is not a multiple of B. Let R0 equals C. R0 equals C and R1 equals B. Choose these integers in this way and apply the division algorithm. What is division algorithm? A equals BQ plus R, like that. Repeatedly to obtain a set of reminders R2, R3, etc., Rn and Rn plus 1 defined successively as the relations What is R naught? R naught equals R1 Q1 plus R2 with the 0 less than or equals R2 strictly less than R1. R1. What is R1? R1 equals R2 Q2 plus R3 with the 0 less than or equals R3 strictly less than R2. Like this, Rn minus 1 equals Rn minus 1 equals Rn Qn. Rn minus 1. What is Rn minus 2? Rn minus 2 equals Rn minus 1 Qn minus 1 plus R, where 0 less than or equals Rn strictly less than Rn minus 1. And what is Rn minus 1? Rn minus 1 equals Rn Qn plus Rn plus 1 here such that Rn plus 1 equals 0. Then here Rn is known as, or Rn is nothing but that's a non-zero remainder, and in this process the GCD of R0 and R1 is this R, or GCD of this integers A and B is R. This is Euclidean algorithm. Means there are number of integers. If you repeated the process of divisibility, then you have number of integers R1, R2, R3, etc., Rn and Rn plus 1 such that Rn plus 1 equals 0. Moreover, this Rn be the GCD of A and B. So this is the statement of division, Euclidean algorithm. How to prove this one? Consider the last case. Here Rn plus 1 equals 0. If Rn plus 1 equals 0, we have Rn plus 1 equals 0. Rn plus 1 equals 0 means this, the last term relation become Rn minus 1 is Rn into Qn. Rn minus 1 is Rn into Qn. Rn minus 1 is Rn into Qn means Rn must divides Rn minus 1. Rn divides Rn minus 1. Okay. Rn divides Rn minus 1 means this Rn minus 1 equals A into Rn. Whatever may be. Okay. So, whatever the next, that is the last but one relation, Rn minus 2. So, Rn minus 2 equals, what is Rn minus 1? A into Rn into Qn minus 1 plus Rn. So, that equals, which is, yes, it is Rn into A into Qn minus 1 plus 1. So, that means this Rn minus 2 also divides Rn, since Rn is a, there is a, Rn divides Rn minus 2. Rn divides Rn minus 2. Why? Because Rn minus 2 is a linear combination or the multiple of Rn. Okay. So Rn divides Rn minus 1. Rn divides Rn minus 2. If you repeatedly like this, then Rn divides Ri for all I. Rn divides Ri for all I. Okay, Rn divides Rn minus 1, Rn divides Rn minus 2, Rn divides Rn minus 3, etc. and so on. Clear? Okay. Now, in particular, this Rn divides Rn, Ri, but I equals 0. Rn divides R0 and Rn divides R1. Why? Because Rn divides Ri, that is true for every I. That means Rn divides A and Rn divides B. That means this Rn be the GCD of A and B. Oh, this is a common divisor of A and B. Okay, Rn be a common divisor of A and B. Then to show that this Rn is a greatest common divisor. Here we know that Rn is a divisor of A and B. When Rn divides A and Rn divides B, means Rn be a common divisor of A and B. Now to show that this Rn is a greatest common divisor, GCD. How? Let GCD of A and B is D. GCD of A and B is D. Now what is A? A equals it is BQ1 plus R2. Here, first relation R0. R0 is R1 Q1 plus R2. Here R0 is A, R1 is B. So it is A equals B1 Q1, B Q1 plus R2. Clearly, A and GCD of A and B divides is D means D divides A and D divides B. D divides A and D divides B. So D divides A, D divides B, that means D divides R2. Similarly, you can show that this D divides R3, etc. and so on. Agreed. So by induction, we have D divides Ri for all I. So this D is there. If D is another divisor of A and B, then this D also divides this Rn. That means this Rn is a greatest common divisor. Okay. D divides Ri for all I means this D divides Rn. Why? Because Rn divides Ri. Okay. So Rn is a common divisor of A and B. If there exists another divisor D of that A and B, that D also divides this Rn, then this Rn is a greatest common divisor. So this is the Euclidean algorithm. Okay. So Euclidean algorithm is if you repeatedly applies the division algorithm, then finally you will have this relations. Here Rn plus 1 must be 0. Why? Because it is a non-negative decreasing sequences. Then Rn plus 1 equals 0. Okay, if Rn plus 1 equals 0, then we have Rn divides Ri. In particular, Rn divides R0 and R1 means Rn divides A and B. Therefore, Rn is the common divisor of A and B. Now remains to show that this Rn is the greatest common divisor. If possible, there exists another divisor D. Then finally we have this D divides Ri and D divides Rn. Therefore, this Rn must be a greatest common divisor. So this is our requirement. Okay.